so in the section 1.3, we reviewed some concepts used in statistics, right? So the idea of probability and probability density. We said that the sum of all probabilities when we are dealing with a discrete quantity is 1, no? So sum when we are dealing with a discrete quantity. When we are dealing with continuous variable, then we have the probability density, and now instead of a sum, we have an integral, and this integral has to be 1, right? We also talked about how to compute the mean value of the quantity that we are studying, standard deviation, variance, and so on. Now, we are coming back. So this was section 1.3. Now we are going to come back to quantum mechanics, and we'll be talking about section 1.4. The title of this section is normalization. And what does it mean? Well, in quantum mechanics, what plays the role of probability? As we already said, the absolute value squared of the wave function, right? So this is the probability for finding the particle at position x at time t. Now, to be more precise, this is the probability density to find the particle at position x at time t. So this is now our probability density. Now, so this is now equivalent to this rule that we are talking about when we are dealing with continuous variables. Very good. So since this is probability, we need to have this equation satisfied. The integral of this probability density in the whole range available to this system has to be 1. Okay, so this equation here has in it the idea of normalization. Whenever you're giving a wave function, you have to be sure that this is guaranteed. Only functions that can give us this result are the functions that we are interested in. Only functions that satisfy this equation are the ones that have physical meaning. This equation, or these functions, these functions are known, we say that these functions are square integrable. So the square, the absolute value square of the function, the integral of this absolute value square gives us a finite number, and we can force this finite number to be 1 because we are talking about probability. Now, if you are ever given a function and you try to solve this integral, but you do not get a finite value, now the integral explodes, it becomes infinite, well, then you discard this wave function. This wave function is not going to be physical, it's just a mathematical function, but with no physical consequence, okay? So we need to guarantee that our function is normalized and that our function is then square integrable. Okay. There is a problem that I'm going to solve with you, problem 1.4. There will be a video available for it, where there is an example of how we can force a given wave function to be normalized. Okay. Now, the question that now comes is, okay, so suppose we have a wave function at a certain time, let's say t1, we check, we guarantee it's normalized, and then the question comes, what will guarantee that a later time, t2 or an earlier time, it's still normalized? Well, Schrödinger equation guarantees that. Okay, so we just need to check that the wave function is normalized at one certain time, and we can then be sure that it is normalized at any other time. So usually when we solve problems, as in this example of this problem 1.4, what we check is the wave function. We check whether the wave function at time 0 is normalized. If it is, then we are sure that it is normalized at any other time. So Schrödinger's equation guarantees that the function remains normalized. Now let's see how. Okay, so the section 1.4 tells us, explains to us mathematically how Schrödinger's equation guarantees that if the wave function is normalized at a given time, for example, at time 0, it will be normalized at any other time t. Okay, so normalization means that this integral is 1. So if this integral is 1, normalization is guaranteed at a certain time. What I know for sure is then that the derivative of this integral, since this integral gives us 1 as answer, the derivative of this integral will be 0. That's going to be our starting point to show that if it is normalized at a certain time, it will be normalized at any other time. So that's our starting point. Now, some details here to notice. Once we solve this integral, we get rid of x. Now, so this becomes a function of time. And then if it was not a constant, it would be a function of time. And so only of time. So that's why here we have total derivative. Okay, but now I'm going to put this derivative inside the integral. And inside the integral, the function depends on x and on time. So this total derivative, once I put it inside, now once I put inside the integral, it will become a partial derivative. Okay, so let's continue with this. We then have our integral. Now we put the derivative inside and you see it's partial, and we have the absolute value square of the wave function. Okay, what is absolute value square of the wave function? Well, remember that we already talked about this. No? The absolute value square means the complex conjugate of the function multiplied by itself. All right, and I'm going to do the derivative of this. Okay, so let's do that. We have our integral, and now I'm doing this derivative of this part. So what do we have? We have the complex conjugate and the derivative of psi, plus the derivative of this complex conjugate and the psi. Okay, all that is inside this integral in x. Okay, now that's where it's the point where Schrödinger's equation is going to show up. Remember, Schrödinger's equation involves this the derivative of psi. Now it's the equation that tells us how this psi evolves in time. So what was Schrödinger's equation? I'm going to write it here. Right, so the derivative in time, and then we have the second order derivative in x. Okay, so I'm going to isolate just this part, pass to the other side this I and this H bar. So when I do that, this H bar comes down here, the I and the H bar comes down here, and also here. Okay, so this part now disappear. What else do we see? Well, there is H bar here and here we can cancel. And when I is in the denominator, I can bring it up to the numerator by changing the sign. Okay, so let me get some space to remind you of that. So if I bring this I here to the numerator, it becomes minus I. Since there is a minus I here, it becomes plus I, H bar over 2m. Okay? And the same thing on this term, since I'm bringing this I to the numerator, it becomes minus I. Why? Look, if you don't remember this, you can check. How do we bring something to, so suppose I have this ratio. How do I bring the term in the denominator up? Well, I'm going to multiply the numerator and the denominator by I. So I see the I now on top, but here I multiplied by I is -1. So that's why this gives us this minus sign when we bring the I to the numerator. Okay, so, but the important thing here is this derivative, I'm going to substitute with this term. Okay? So let's continue with that. We have the integral, we have this conjugate, and now this derivative, we are going to use this term. So we have IH bar over 2m, the second order derivative minus IV psi and H bar. Okay, very good. It's long, but it's not complicated. You just have to be careful that you're not going to make any mistake or forget any term as you write this. What are we going to do now with this other derivative? The same thing, but here we are playing with the complex conjugate of the wave function. Okay, so this term here, what will it become? I'm again using Schrödinger's equation, this equation here, just as we did before, but now we have to do the complex conjugate of all that. So we have to do the complex conjugate of this part. Complex conjugate of the I will give us minus I. H bar is just a real number. Number 2 is real, mass is real, so nothing there. Here we have derivative in x, so nothing changes here, but the psi is the complex conjugate. Let's now go for the second term, this term here. We have a minus sign there, okay, but the I, the complex conjugate of the I will become minus I, so minus with minus gives us that plus. H bar is just a number. The psi here is the complex conjugate, and you see that I'm waiting some time to talk about V. Remember V here is the energy potential, no, the potential energy. When we are dealing with conservative systems, no friction, no losses involved, this potential energy is real. So when I do the complex conjugate, nothing changes. It remains V. Okay, but there is a problem at the end of this chapter where we could play with a potential that is imaginary, okay, or complex, but this is not the case here. All right, so all that I did was to write this piece, and I had to remember to put my function back. Okay? And all this, cannot forget, is inside this integral from minus infinity to infinity. All right. Now let's examine what we have in this integral. Because we said that the V, the potential energy, is real, you see that this term here and this term here are equal. So let me rewrite this term so we can see it easily. We have minus I V H bar. We have this function and this function. Okay. So this is this first term. Now the second term there, we have plus I V H bar, the function and the function. So they are equal. This term and this term cancel. Okay. We can move. You see that the function here was before V, but I can move them around because these are all functions of x. Okay? So the only thing that remained now inside this integral is this term that involves the I, H bar, and 2m. So this is just a constant, right? So I'm going to put it in front of this integral, not I, H bar over 2m. And let's put inside the integral what really depends on x. So it is this psi, so let me write it here. And this second order derivative, we have it here. From the second term, we careful, don't forget that there is a minus sign here, right? So here I have to remember to put this minus sign, and then we have the IH bar is already in front. What remains is this second order derivative, and don't forget that there is a function here, right? So let's put it there. So this is what is still inside the integral from minus infinity to infinity. All right, so let's continue now with this. Now comes a very nice trick. Look at what we are going to do. We are going to rewrite this integral like this. Well, we have this constant in front, and inside this integral, look at what we are going to do. I'm going to write it as this derivative of psi, first order derivative, minus first order derivative, and psi. Can I do that? Well, you will say, wait a second, is this correct? I can see that we recover the second order derivative here. That's okay. But how about the other term that we have, and I'm going to rewrite it here, the other term that we have, which is when I do the derivative of this first term. So we have this, which was not in the equation above. And okay, we have this, which yes, it was in the equation above. Okay, so what are we going to do with this term here, which was not in the equation above? Well, let's have a look at this second term here, okay? So we have minus, when I apply this derivative here, we have minus the second order derivative, just as we had above, so this is good. But we will also have the integral of this guy, which gives us minus first order derivative and first order derivative. So this term here was not above. So how is this possible? Well, look at this. This term was not above. This term was not above, but they cancel each other. This is positive, this is negative. So what I wrote at the bottom here is exactly the same thing as we have above here, okay? And why this is a very nice trick? Because integral of a derivative is just integral of the derivative of a function is just the function. Okay, so the solution of this integral is now I h bar over 2m, and the integral now is solved. What survives here? That function inside. Okay, so very nice. We got rid of the integral. The integral goes from minus infinity to infinity, so we have here from minus infinity to infinity. Now comes a very important concept that will allow us to finally solve what we have here. Whenever we are dealing with square integrable functions, the functions which are interesting to us, the functions that can be normalized, the function that can really give us information about probability in quantum mechanics. So the functions that can, the functions that will guarantee that this is one, okay, that this integral is not going to explode. In these functions, what we know for sure is that at minus infinity and at plus infinity, this has to go to 0. If it does not, then when you're trying to solve this integral, it would explode. Okay, so the function has to go to 0 at minus infinity and at plus infinity, the derivative of the function as well. At minus infinity and plus infinity, it has to go to 0, okay? And the same thing about the complex conjugate. So because of this property, because we are only dealing with functions that can be normalized, what we have in this line is equal to 0. See, the integrals are from minus infinity to plus infinity, so this has to be 0. Okay, so why is this good? We proved what we wanted. Okay, so if we are dealing with a function that is square integrable, let's go all the way up. As we said, if we are dealing with a function that is square integral, that gives us 1 here, then the derivative of this is 0. And that's exactly what we proved here. Okay, so, and we proved that using Schrödinger's equation to get at this point. So this is to say Schrödinger's equation guarantee that if the wave function is normalized at a certain time, it will be normalized at any time. Okay, so usually what we do, we check whether it's normalized at time 0, and then we are comfortable, happy, knowing that it will be normalized at any other time. Okay, so what I'm going to do in the next video with you is solving this problem 1.4 to show to you how we check whether the function is normalized at a certain time 0.